You plug a 1605 Hz high refresh rate monitor into your Linux rig next to an older 75 Hz screen. You expect smooth motion, but as you drag a window between them, the image severely stutters and tears. Meanwhile, a rogue application running in the background logs every keystroke of your password. Because of how the desktop is built, the app siphons your data without triggering a single system warning. A graphics bottleneck and a keyboard logger have a single point of failure: the X11 display server. This is the engine that manages everything you see and interact with on the Linux desktop. X11 was designed in 1984, built for an era of thin clients and basic networking. This was decades before 4K video, fractional scaling, or modern browser-based exploits were even concepts. While our hardware has evolved at light speed, the Linux desktop relies on a 40-year-old middleman that was never intended to handle a modern graphical workload. This diagram shows X11 acting as a central broker. For an application to display anything on your screen, it must first send a request to this central X server. Trace the path of a single drawing request. The application talks to the X server, which talks to a separate window manager to see where the window belongs, which then sends instructions back to the X server before the pixels finally reach your hardware. This specific architecture creates a fatal security flaw. The X server grants global access by default. Applications aren't isolated from one another. In this diagram, you can see how any connected app can see the inputs and data of every other block on the server. Because the middleman doesn't verify permissions for every request, one app can inject fake keystrokes into another, or take screenshots of your entire desktop without you ever knowing. Patching these holes is a losing battle. To fix the lag and the security risks, the 1984 architecture has to be removed entirely. In 2008, developers began work on Wayland. They started with a radical premise: stop using a middleman and let applications speak more directly to the system. This diagram illustrates the Wayland architecture. It combines the display server and the window manager into a single entity called the compositor. This collapses the old looping communication path into a direct line. In this direct pipeline, apps render to their own memory buffers and hand them to the compositor. This removes the synchronization errors that cause screen tearing and allows monitors with different refresh rates to run at their full native speeds. Security is built into the connection itself. Wayland enforces strict client isolation, meaning applications are sandboxed and cannot snoop on each other's inputs. If an app wants to record the screen or capture input, it must ask the compositor. This triggers a user-facing prompt, ensuring you remain in control of your data. By removing the global access in X11, Wayland addresses security at the architectural level, while the streamlined data path ensures frames reach the monitor without the overhead of a middleman. The biggest obstacle to this transition is compatibility. Users don't want to lose access to the thousands of Linux applications written over the last few decades. To bridge this gap, developers created X-Wayland, a compatibility layer that allows older software to run on the new system. This structural diagram shows how it works. X-Wayland runs a localized X11 server as a standard, isolated client inside the secure Wayland environment. Your legacy apps think they're on a traditional desktop, but they remain safely sandboxed. Development on the original X11 server has essentially stopped. The project is now in maintenance mode, receiving only critical security patches. Major desktop environments like GNOME and KDE Plasma have officially made Wayland the default, signaling the end of the transition. Wayland replaces a 40-year-old architectural bottleneck with a design that enforces security by default and supports the full performance of modern graphics hardware.